Welcome back to this lecture. As we were talking, we are going to start with another problem of laminar flow in pipes. The question says that the crude oil of viscosity 0.9 poise and specific gravity 0.8 is flowing through a horizontal circular pipe of diameter 80 millimeters and length of 15 meter. Calculate the difference of pressure at the two ends of the pipe if 50 kilograms of oil is collected in a tank in 15 seconds. So, we are knowing this is mu, okay. This is specific gravity, S is 0.8, right. So, we know the diameter is 80 millimeters and the length is 15 meters. So, going back to we are going to have a white screen. Okay. So, as always what we are going to do, we are going to write the things that are actually given. Given thing is mu is 0.9 poise or in SI unit is 0.09 Pascal seconds. We know specific gravity S as 0.8. Okay. Therefore, the density is given to be 0.8, and if we assume 1000 kilogram per meter cube density of water, so the density of the fluid is 800 kilogram per meter cube. Okay. Since S is rho by rho water. Okay. Diameter we know it's 80 millimeters or 80 into 10 to the power minus 3 meter. R we know 40 into 10 to the power minus 3 meter, and length L is given as 15 meter. Alright. So, these are the things that we already know from before. So, first we are going to do, we are going to calculate the volume of oil collected in a tank in 15 seconds is equal to mass of oil collected in 15 seconds divided by density of oil, and that is going to be 50 divided by 800, that is 0.0625 meter cube. This is the volume of the oil that is collected in a tank in 15 seconds. Therefore, discharge Q is equal to volume by time equal to 0.0625 divided by 15. Q is 4.17 into 10 to the power minus 3 meter cube per second. See, calculate the area of the pipe. Area of the pipe is pi d square by 4, and that is pi by 4 into diameter was 80 into 10 to the power minus 3, and this gives us 5.026 into 10 to the power minus 3 meter square. So, the average velocity is Q by area, and this will give us 4.17 into 10 to the power minus 3 divided by 5.026 into 10 to the power minus 3 is equal to 0.83 meters per second. All right. Therefore, we will find the Reynolds number, that is rho V average into d by mu, and this rho is 800, V average is 0.83, diameter is 80 into 10 to the power minus 3, mu is 0.09. This is actually very important to check, and this comes to around 590. So, as Reynolds number is less than 23, the flow is laminar. Okay. So, we are going to do the again white screen. Yes. So, we have established that flow is laminar. Therefore, Q is going to be the formula that we have derived, minus pi divided by 8 mu dp dx into r to the power 4. So, Q value we already know, that is 4.17 into 10 to the power minus 3 is equal to minus pi 8 into 0.09 dp dx into r we know 40 into 10 to the power minus 3 to the power 4. What we get is dp dx is equal to minus 373.32 Newton per meter square per meter. This means this is the dp dx and it is constant. So, the pressure difference per unit length is minus 373.37. If we assume P2 pressure at one end and P1 at other and length is 15, this should be equal to dp dx equal to minus 373.32, implies P2 minus 1, the pressure difference between the both end is minus 5599 Newton per meter square. So, this is the final calculation. Okay. This was the difference of pressure. So, that came out to be finally, I will write here, P2 minus P1 came out to be minus 5599 Newton per meter square. Okay. So, this is how we solved a detailed solution. All right. So, I will take down this ink. So, now we have done the laminar flow through the circular pipe. Now, we are going to see the laminar flow between the parallel plates. So, this is a parallel plate. Okay. So, whatever assumptions that we have made for laminar flow in pipes are valid here also. In this case, both the plates are fixed plate, and this is also fixed plate. As you can observe, this is x direction and this is y direction. Okay. The distance between the plate is given by t. The flow is in this direction, positive x axis, and what we have assumed is an element having the thickness, this length is delta x and this is delta y, this direction. Okay. and we have written all the forces in a similar fashion as we did it for the pipe flow. So, if the pressure is P here, so the force by per unit meter is P delta y from this side. If the pressure, if there is a pressure gradient dP dx, so over the length delta x, the pressure will become P plus delta P delta P by delta x into delta x. This will be multiplied by the area delta y into 1, because we have assumed a unit length in the other direction. Similarly, T delta x, force is the force per unit meter per unit length, and if we assume that the shear stress is increasing in this direction by delta T delta y, so this is the force in the other direction. Okay. So, as you can see, pressure force is acting in this direction, pressure force is acting in this direction. On the bottom side, this is the shear force is acting in negative x direction, and here it is acting in positive direction. So, with this in background, we start to write the force, or we do the force balance analysis along the flow direction. So, for your convenience, I have made the free body diagram that is there, I have just reproduced in the right top corner. Okay. So, you see P delta y, that is force per unit length, minus this one here, and this again is in the negative direction T delta x. So, minus T delta x, and this is in positive direction. So, this is plus, and that all equals 0. Okay. Now, if we divide both side by delta x into delta y, that is area, what we are going to get is, so this becomes P delta x delta y, and this also become P delta x into delta y whole square. So, this will get cancelled here, here. So, if you do these cancellations, what we are actually left with is dP dx here and dt dy, rest of the things will get cancelled. So, this is one important equation that we are going to get. So, dP dx is equal to dt dy. Now, this is again a laminar flow assumption. Okay. And also we will also assume that the mu, the viscosity, is constant. So, it will be d square u by dy square is equal to 1 by mu dP dx. This is the equation that we get after we put in this. Okay. All right. This is equation 8. Now, because here it is double integral, so we will integrate it twice. So, we will get u is equal to 1 by mu dP dx into y square by 2 plus C1y plus C2, because we have assumed y, you see y is in this direction, right. All right. So, this is the equation we get. Now, the boundary conditions are u at y is equal to 0, the plate is fixed. So, due to no slip condition, the velocity will be 0. Also at the thickness at the other end after the distance t, also because of no slip condition, the velocity is going to be 0. And if we use these boundary conditions in equation 9, we get u is equal to minus 1 by t minus 1 by 2 mu dP dx into ty minus y square. So, I will just quickly try to tell you how it is done. We know at, so that you are able to repeat it at home. So, what we say, u at y is equal to 0 is 0. So, in this equation we know at y is equal to 0. So, put this u is 0 at 1 by mu dP dx, y is 0 square by 2 plus C1 into 0, right, plus C2. this will give C2 is equal to 0. And if you do u at y is equal to t, so u at y is equal to t is also 0, right. So 1 by mu dp dx, and y here is t, so t square by 2 plus C1 t, because we already found out C2 is 0. This is how you will obtain C1. C1 is going to be minus 1 by mu dp dx t by 2, and you substitute t and C1 and C2 in these equations, and this is how you end up in this y, okay, sorry, this u. So, this is the final equation for u after substituting the boundary conditions. This is also something that you can try to remember because it is quite simple. Okay. Here also the velocity distribution is parabolic. You see, Ty minus y square, parabolic in nature. Okay. This is how it looks. Now, repeating the same procedure of average velocity, maximum velocity and discharge. The average velocity is again given by integral 0 to t u dy by t, and if you put u as obtained in the last slide here, what we are going to obtain is minus 1 by 12 mu dp dx t square. I would say please do this as homework exercise. If you have any problem, message me on forum. Okay. All right. And you don't, not only this V average, but I request you to also do this for the flow through the pipes that we covered in the last lecture. Okay. Now, you see the velocity profile is parabolic, right. This means the maximum velocity again is at the center line, which is y is equal to t by 2, and if we obtain y is equal to t by 2 in the equation that we obtained in the equation number 10, okay, then we can get u max, which comes out to be minus 1 by 8 mu dp dx into t square. My recommendation is also try this, okay, and if you are unable to, contact me on the forum. All right. So, if you divide u max by V average, what we get is actually u maximum is 1.5 times V average. In the pipe flow it was, u max was 2 times V average. Here it is 1.5 times the V average, okay, and Q is simply V average into A, all right. So, V average we already know 1 by 12 mu, and the area is simply T, correct, because we are considering the per unit length. So, that we multiply the per unit length T, so that becomes T square become T cube, okay. So, these are some of the formulas that you must be remembering. Now, we will solve one problem from this. So, the question is, determine the pressure gradient, the shear stress at the two horizontal parallel plates, and the discharge per unit width of the laminar flow of a liquid with maximum velocity of 2 meters per second between the two horizontal parallel fixed plates which are 100 millimeters apart. we assume that mu is equal to 2.4525 pascals per second. Okay. So, to solve this any problem, what we do is we simply write first the things that we know from before. So, I will just start writing down. First we write out the things that are given. Okay. Given is the flow is laminar. Okay. U max is given as 2 meters per second. Thickness is given as 100 millimeters or 0.1 meters. Mu is given as 2.4525 Pascal second. Now U max is 1.5 V average. This is which we have found out, implies V average is going to be 2 divided by 1.5, that is 1.33 meters per second. Okay. So, for laminar flow between two parallel plates, V average is equal to minus 1 by 12 mu dp dx into t square. We simply start putting in the values of V average. Minus 1 by 12, mu is 2.4525 as given in the question, dp dx we do not know and thickness we know, 0.1 square. This will on solution, if you use the calculator, you will get dp dx is equal to minus 39142 Newton per meter square per meter. So, this is the first part, I mean where we first thing that we do is we obtain dp dx. Now, what I do is choose the white screen again for the another part. Okay. So, here we have approximated the value of I will just take the value of V average as 1.33 meters per second. Okay. All right. But if we use V average is equal to 4 by 3, which is 1.33 meters per second, we can get, I mean I am just trying to show there will be slight difference, of course not that much, but it will be minus 3924 Newton per meter square per meter. I mean very almost not very difference. So, now we know that U is minus 1 by 2 mu dp dx into ty minus y square, right. So, du by dy will be minus 1 by 2 mu dp dx t minus 2y and du by dy at one plate will be equal to minus 1 by 2 mu into dp dx into t. All right. For tau naught at the wall is going to be mu du by dy at y is equal to 0. So, tau naught is going to be, okay, this tau naught I will solve on the next sheet. So, sorry, first let me do the eraser. Okay. So, I am choosing another sheet now, white screen. So, tau naught is going to be writing that equation again, mu du by dy at y is equal to 0, which we have already actually calculated. Therefore, tau naught is going to be 2.4525 into minus 1 by 2 mu dp dx into t, or tau naught is equal to 2.4525 into minus 1 by 2, 2.4525, and dp dx was minus 3924 into 0.1. So, tau naught is coming out to be 196.2 Newton per meter square. Okay, now discharge per unit width. Q is minus 1 by 12 mu dp dx into t cube. Therefore, Q is going to be minus 1 by 12 into 2.4525 into minus 3924 into 0.1 whole cube. So, Q is 0.133 meter cube per second. Okay. All right. So, I will erase all the ink here. Okay. So, final answers is going to be, the first one is pressure gradient that was required, dp dx came out to be minus 3924 Newton per meter square per meter. Second one was shear stress at the plates, that is tau naught is equal to 196.2 Newton per meter square, and the third one was discharge per unit width Q, meter cube per second. So, these are the final answers. So, I am going to the, so this was the problem that we have solved now. There is one more problem, but I think it is nice time to end this lecture here, and we will resume our next lecture by solving this problem. Thank you so much, and I will see you in the next lecture. Bye.